Okay, I want to tell you about Gauss's law and concentric shells, how you handle problems that involve concentric shells. One of the big things is just trying to figure out the setup that's being described. So let me describe this setup. These aren't circles, these are spheres. And it's basically two spheres. You got a solid sphere of metal that is a radius A, that's a radius A, and it's charged up Q. The net charge on it is Q. And then you have some air right in here, where that's an insulator. And don't ask me how this is being suspended in there. We'll maybe we'll figure that out at a later time, but it's just like hovering in there. And then it's inside another sphere. Now this is a hollow sphere, but it's got the wall of the sphere has some thickness. So there's the metal. So that's the thickness of the outer sphere. Now the inner wall of the outer sphere is B, and the outer wall of the sphere is C. And we have to keep in mind that these are spheres now. All right. So this is what we're going to do. We're going to take and ground the outside of this. We're going to touch this with a grounding wire. And what that will do is it will cause the charges to redistribute on here. And so let me explain. If this is positive Q, then it's going to pull in some charge, some negative Q here. So we can expect there to be some negative Q right here on the inside. And not only that, but then if you'd think that there'd be positive Q on this outer side, on the outer surface, but if I ground that, if I attach a ground there, electrons will come up and negate that. And so there'll be no net charge on the outer sphere because the electrons will come up and negate all this positive charge. So again, what I did was I grounded the outer part, and that caused there to be no charge here. There's no charge on the outer part, but on the inner side, there's still the negatives that are being pulled in by the positive Q. All right, so let's see. Let's find out what the electric field will be at all these locations. Let's find the electric field at a distance that's less than A away. Okay, well, the electric field at R is less than A is going to be, since you're in the metal, that has to equal 0. So at R equals less than A, the electric field is equal to 0 because it's inside the metal. And any metal that's in equilibrium, it has no field in it. So don't have to apply Gauss's law. We just know because this is inside the metal. Okay, then let's find what the electric field is where between here, like right here. What's the electric field in that region? So we'd like to find the electric field at, let's see, R is greater than A, but less than B. I'd like to find it at R is greater than A, but less than B. So what I'm going to do is I'm going to draw a Gaussian surface. It's going to be a spherical surface. It's going to be like that. And I'm going to apply Gauss's law. So let's see, I'll go Q enclosed over epsilon naught is equal to the closed surface integral of E dot dA. Remember, two ways to find the flux through a closed surface is this way and this way. These are two ways to find the net flux through a closed surface. Well, the net charge enclosed is Q. That's all the charge that's enclosed. And then over epsilon naught. So I'm done with the left side. Now the right side, if you look, E is outward. E is going this way. And the DAs are outward too. So if I snuck in there and looked at a DA, it's going normally outward. The DAs that make up the Gaussian surface. Remember, this is the E on the Gaussian surface and the DA of the Gaussian surface. And so I can get rid of the dot product because E and DA are in the same direction. I can also pull the E out of the integral because E is the same amount at each point on this Gaussian surface. And so when I pull the E out, I'm basically just summing up all the DAs. And so I have E equals, when I sum up all the DAs with the integral, 4 pi times r squared, where r is the distance from the center all the way to the Gaussian surface. So the electric field is going to be Q over 4 pi epsilon naught r squared. That's the same as for a point charge. So when you're out here, it's the same as if this were just a point charge just right at the origin, right at the center. Okay, now let's see if we can't find the electric field at the next location, which is right in the metal. Okay, so the electric field inside here, right here, remember there's a charge Q here. The electric field is at R is greater than B, but less than C. So somewhere in that region, the electric field has to be, that's what we're after, and that has to be equal to 0. And that's because it's in the metal. Because inside metal, E is 0. If it weren't 0, the charges wouldn't be in equilibrium. They'd be moving around. Remember our argument for that? All right, so we know that. And then how about outside? What about E when you're at R is greater than C? R is greater than C. No, R is greater than C. Excuse me. So out here, and so if you put in a Gaussian surface out there, the charge enclosed, let's see what it is. The total charge enclosed is going to be, let's see, we have, since we have Q here and negative Q here. And so that's going to be, the total charge enclosed is 0 over epsilon naught is equal to the net flux. So since there's no charge enclosed, there can't be any flux through this surface. And since there's no flux through this surface, there can't be any E there. So E is equal to 0 out there when you're out a distance there. Okay. They're also going to ask you how you know what the charge is on the inner surface. I'm telling you that it's negative Q, but let me show you the proof of that. If I were to draw a Gaussian surface here, see that Gaussian surface in there? Right inside the metal? There can't be any flux through that Gaussian surface, the one I'm pointing to, because there's no E there. So like if you do E dot dA at every point on this Gaussian surface, since there's no E, there's no flux. Well, if there's no flux, that means that this side of the equation is 0. That's a big 0. So that also means that Q enclosed over epsilon naught is 0. So what has to be the net charge enclosed? It has to be negative Q. So those are going to be exactly equal in magnitude but opposite in charge. Okay, I'm going to need one more video for this one. All right, see you in a bit.